All right, so good morning, everyone. Today we're going to start with the new lesson, and this time this is about circular motion. And again, we're still on motion in 2 dimension. All right. So first, before we start with the concept, let us try to be familiarized with some common terms first about circular motion. Okay. So the first one is the axis of rotation. All right. So what is the axis of rotation? Now, when we say axis of rotation, this is the point or more of a line that is the center of the circle. Okay. So that is the axis of rotation. This is actually an invisible line. Okay. An invisible line along the center of the circle. All right. So this line in here is called the axis of rotation. Okay, let me use my pen. Okay, so this line here, which is actually an invisible line, is called the axis of rotation. Okay, that is the first term. Another one is we have, okay, the other one is if the axis of rotation is inside the object. Okay, we say that the object is rotating. Okay, so like the one as you can see here with the earth in here. So the axis of rotation is inside the object. So we say that the earth in here is rotating around its axis, right? The earth is rotating around its axis, or spinning, in other words. Right, number 2 here, this one here is also rotating. If we have an invisible line here, so we can say that this device is also rotating. Okay, also rotating on its own axis. Okay, so that's the second term, axis of rotation, and then rotating, because we need to identify this one, because there's another word which is called revolving. All right, revolving. Now, if the axis of rotation is outside the object, okay, we say that the object is revolving. All right, revolving, like this one. I think this is a table. Okay, table revolving. Okay, so we have here this one. Let's say they're following a path. Okay, or an orbit. Right, they're following an orbit or a path, and they are revolving around something here at the center, right? So we say that this is revolving, right? Okay, how about I have here, okay, which one is revolving and which one is rotating, do you think? Okay, which one is revolving and which one is rotating? Okay, where is, this is M4, where is Cam? Hello, Cam. Today is 27, 8/27. Hello, Cam. Cam, can you turn your mic on, please? Hello, Cam. Which one in here, you can identify them with colors, the yellow and the blue. Which one is rotating and revolving? Okay. Cam. Again, please. Revolving and rotating. How do you differentiate that in here? By the way, can you see the slide, Cam? The blue one? Okay, are you seeing the slide? All right, Cam. How do you differentiate here between rotating and revolving? Okay. How about the blue one? What is it doing with in terms of the yellow one? Is it revolving or rotating?
Revolving.
Revolving. Okay. And what is rotating?
Yellow.
Yellow. Yellow is rotating. All right. So the blue one is revolving around the yellow one. Tama ka, Cam? The blue one, let's say if the blue object is revolving around the yellow object, right, Cam? The blue one is revolving around the yellow object. Okay, but the blue one is also rotating around its, what do you call this line here again, Kem? What do you call this line? At the center or at the middle of the blue object, Kem? What do you call this line, invisible line again?
Let me fill up the line.
Baimon is singing. I will call Baimon.
No.
Baimon, what do you call this line here? The invisible line at the middle of the blue object. What do you call this line here? Baimon. Baimon, turn off her microphone. All right. So this one, hello Tale, good morning. Okay, so this one, this blue object is revolving around the yellow one. Okay, the yellow object. Chamikap, that is revolve. Okay, revolving. But this blue object is rotating.
Teacher, are you sure?
Yes.
Are you sure that you draw the red line in the right direction?
I'm sorry.
Is in the red line? Is the red line that you drew a few seconds ago the right direction, teacher?
Yes.
Okay, good.
Okay, so this one is the red line. Yes, the red line, or say that an invisible line, is the axis of rotation, and therefore, if as you can see here, we have an arrow here, a green arrow. It means that this object is rotating around the red line. Okay, rotating around the red line, and the red line here is called the axis of rotation. Okay, take note about the difference between rotating and revolving. Okay, Nakap? So the difference between revolving and rotating. Rotating, if the line is inside, okay? The line is inside. Okay, so rotating and revolving. Another one we have here is what we call a linear or tangential velocity. Okay, what is this? Objects moving in a circle. Okay, even though it is a circle. Okay, now if an object is moving in a circle, it still has a linear velocity. Okay, linear velocity. And how do we define that? When I say a linear velocity, that is still equivalent to the distance over time, or displacement, change in displacement over time. Okay, so that is the change in displacement over time. That is the linear velocity. Now, but in here, if an object is moving in a circle, this is commonly called tangential velocity. Okay, tangential velocity, from the word tangent. Okay, tangent, since the direction of the linear velocity is tangent to the circle. Okay, let's say this one here, velocity, it's tangent to the circle, meaning it touches at one point on a circle. Okay, that is what we mean by tangent in your mathematics. Check it up. So that's why in here, if the object is moving in a circle, it still has a linear velocity. Let me see if I have here. Okay, so this one, linear velocity. Okay, all right, so this one is the linear velocity. This one, okay, the linear velocity. Next, linear. All right, so aside from that, aside from the linear velocity, also we have rotational and angular velocity. They are the same. Rotational, you can call them rotational or angular velocity. Objects moving in a circle also have a rotational or angular velocity, which is the rate angular position changes. Okay, the rate in which the angular position changes. Okay, that is a rotational or angular velocity. Now, rotational velocity is measured in degrees per second. Okay, degrees per second. But however, we use aside from that, one thing, the common measurement is called radian per second, right? So degrees per second is converted into radian. I think you know that already in your mathematics, right? Radian per second, or you can also have rotations per minute, or sometimes they call it revolution per minute, or RPM, etc. Right? So again, rotational velocity or angular velocity can be measured in degrees per second, but also as equivalent in radian per second, or we also have rotations per minute or revolution per minute. Okay, these are some of the unit of measure of angular velocity or rotational velocity. And the common symbol is this one, a Greek letter for omega, right? That is the symbol. And this one in here is the formula. Okay, rotational velocity or angular velocity is equal to the change in the angle, right? Change in the angle over time, change in the angle over time, which means this one is delta theta. Okay, delta theta, which theta is the angle over time. Okay, over time. And the unit again is radian per second. And then, yes, radian per second in here. Also, you can say degrees per second, or what else? Rotation per minute or revolution per minute. Okay, so we can follow this formula for angular and rotational velocity. Right, next. The next one here is if an object is rotating, okay, all points on the object have the same rotational or angular velocity, right? All points on the object have the same rotational or angular velocity. Let's say this is a ball, and let's say you are holding here at the center. Okay, it means that all points on the object, let's say from here, it has rotational velocity in here. It also have rotational velocity at this point, and also at this point. Okay, rotational velocity. But all points on the object do not have the same linear or tangential velocity. Okay, so it's different. The linear velocity is different from this point and from this point. Okay, because why teacher? Because they have a different distance. Okay, distance from the center. Okay, that's different. Okay, what else? Also, we have here next one, linear velocity of a point depends on this factor. Number one, the rotational velocity of the point. Okay, it means that more rotational velocity means more linear velocity. What do you mean by more rotational velocity? It means that if the object is rotating faster, all right, rotating faster or revolving faster in that case. Okay, on the picture here, in this case, more revolutional or rotational velocity or angular velocity means more linear velocity also. And also it depends on the distance, okay, from the point to the axis of rotation. Okay, let's say from this point up to this point. Okay, it also depends on the distance, right? The linear velocity depends on this distance. It means that more distance from the axis means more linear velocity, right? They will have more linear velocity. And we can have this one relationship between rotational and linear velocity. We can have this one. Linear velocity, V is the linear velocity, equals R, and this one, omega, is the angular velocity, and R is the radius, right? The radius of the circle, okay? So, or the equation. And then we're going to have this example number 1, okay? Example number 1, determine the angular velocity if 4.8 revolutions are completed in 4 seconds. Okay, how do we do that? Example number 1. You are going to determine the angular velocity if 4.8. Okay, it means that an object were able to complete the circle 4.8 times. Okay, 4.8 times in 4 seconds. Okay, so first we need to identify the given. Okay, so what are the given here? Okay, first, we can use this change in the angular displacement. Okay, change in the angular displacement. We know that this one, okay, 1 revolution or 360 degrees is equivalent to 2 pi radians, right? In your mathematics, 360 degrees is equivalent to 2 pi radians. So we need to convert this 4.8 revolution to pi radians. Okay, so that is 4.8 times 2 pi radians. Okay, so that is one of the first given. Okay, next, another one, we also have here the time in second, of course. And then we are going to find the angular velocity or omega. And of course, we can use this formula. Okay, angular velocity is equal to the change in the displacement or angular displacement or delta theta over t. Okay, so how do you solve that? How do you solve that? Anyone? Please try in your notebook following this formula over time. Okay, so we have here 4.8, right? 4.8 times 2 pi radians. Okay, if this is correct, 4.8 is equal to 9.6 pi over 4. Okay, time is 4 seconds. Let's see if we have the same answer. Let's see, maybe I am wrong. Okay, type in the chat box your answer, please. If you have the answer. Let's see, maybe I am wrong in here. Use your calculator to find the value of pi. Approximately, we have 3.14. Okay, you can use 3.14 as the approximate value of pi. Okay, again, 1 revolution is equivalent to 2 pi radians, or that is equivalent to 360 degrees, right? Answer, please, on the chat box. So I can give score here. I can show you. I have a lot of points here. I'm going to count this before the finals. Okay, I'm going to count your score here before the finals. Okay, so I have here Yufa, Kem, Yufa, Kem. Who else? Baimon also, but Baimon have different answer. And Mio also have different answer. Okay. So how do we do that? 9.6 pi. What's the answer? 9.6 pi divided by 9.6 is equal to. Okay, so let me see. What's my answer here? If it is the same with your answer. Okay, 7.50 of 536. Okay, same with Yufa and Kem. Okay, but Baimon, how did you find your answer, Baimon? And Pau also. In meter per second. Okay, you converted this in meter per second, Pau. Can you turn your mic on, please? Pau? How did you get meter per second?
I see a velocity.
Okay, the velocity. Okay, so it should be in radian per second. Okay, radian per second, and we have the same answer with Kem and Yufa, right? Kem and Yufa, right? Thank you so much. This is 7.536 or 7.54 radians per second. We just need to, it's very simple, right? Okay, number 2, example number 2. Okay, let's try this one. Example number 2. Jack climbs on a horse, this one on a horse that is 12 feet from the center of a merry-go-round. Okay, I know you know this one, merry-go-round. It makes 3.25 revolution per minute. Now, you're going to determine Jack's angular velocity in radian per second. Okay, because we have here already angular velocity is 3.25 revolution per minute. Okay, so the question here is that you will just convert this to radian per second. Okay, let's try to answer that on the chat box. So angular velocity, we have 3 1/4, right? 3.25 is 3 1/4. It means 3 round the circle 3 times and then 1/4. Okay, 3.25 revolution per minute. Okay, so how do we do that? Let's see if we have the same answer. 3.25 revolution per minute, and you're just going to convert that in radian per second. Okay, remember 1 revolution equals 2 pi radians. Sa may kap, 1 revolution is equal to 2 pi radians, or 360 degrees is equal to 2 pi radians. Right, on the chat box, please. Let me see. This is what you're going to do. Okay, 3.25 revolution per minute. And then 1 minute equals 60 seconds. And then 2 pi radians is equal to 1 revolution. Right? So convert this one. Radian per second. Okay, so your answer would be how's the answer? Right, Soda has an answer. That is correct, Soda. And the unit Soda is radian per second. Chamikap? Soda, that is correct. Who else aside from Soda? Radian per second. The unit Soda is radian per second. Okay? No more answer? Only Soda? All right, so I'd like to put today, because only very few students are participating, I'd like to put 2 points for correct answer today. 2 points for Yupa, Kim, and Soda, okay, for correct answer. Okay, only Soda. Okay, so the answer is 0.34 radian per radian per second. Okay, radian per second. Now, what if the same problem, but we are going to solve for linear velocity? Okay, linear velocity. Okay, determine Jack's linear velocity. Same problem. Okay, same problem. What is the formula? First, we need to identify the given. The radius is 12 feet, okay? If you want to convert it to meter, okay, you can have 3.66 meters, or in here, it's okay. I will accept feet per second for your velocity. But if you want to convert it to meter per second for the velocity, that would be better, because that is the standard unit of measure, right? So R equals 12 feet equals 3.66 meters. And then what else? The angular velocity that we have solved already, which is 0.34 radian per second. Sorry for the S, radian per second. and you are to find for the velocity, all right, or the linear velocity. So you can use this equation. V equals R multiplied by the angular velocity. Okay, what's the answer? Very easy. Another 2 points. Another 2 points. Why I only have a very few students participating today? On the chat box, please. Okay, so I have Pry, and then I also have Kem. Again, they have different answer, Kem and Pry. You can write the unit, so it would be easy for me. Okay, would it be meter per second or feet per second? Okay, that's a feet per second. Okay, feet per second. The answer of UFA is okay, not 4.08 feet per second. All right. Okay, so let me check because my answer is in meter per second. Let me check. That would be what is that? 12 multiplied by. All right, so your answer would that be feet a poom? Okay, so the answer would be if you just multiply 12 r is 12 and angular velocity is 0.34, that answer would be 4.08. Sa may kap? 4.08. Okay, because my answer here is in meter, but again, you can answer in feet. Okay, so 1.24, who has 1.24 as their answer? Poom. Okay, poom. If that is your answer, that would be meter. Meters per meter per second. May try feet per second. Poom. Okay. And then mu, if that is correct, 1.24 meter per second. Okay. Or you have another answer that is 4. What is that? 4.08. Okay, again, I said I will accept this. Okay, feet per second. All right, it's very easy, right? Very easy to solve for linear and angular velocity. Okay, do you understand? Let me just record this one, and then let's have a short quiz about this one, just to linear and angular velocity. Okay, let me have some point for Pry. Who else? Kem. And then Yufa. And then Not. And then Miu. Not. And then Miu. Where is Miu? Okay, Miu. Poom. And then Tan. Poom. And then Tan. Do you have a question before I give you the